All right, our next speaker is Andrew Knightly from the University of Maine, and he will give us a talk with the title Trace Formulas for Locally Supercuspidal Cusp Forms.
Thank you very much, Florian and Claude, for organizing this nice conference. Oops, let's see. Okay. So the topic of my talk is, or the object of study are cusp forms. So these are classical holomorphic cusp forms on the complex upper half plane. Sk of m is going to denote the cusp forms of weight k and level m. This space has some redundancy built into it coming from the old forms. So we'll let hk of m be the set of new forms. So these are the cusp forms not coming from spaces of cusp forms of lower level. And sk new is the span of the new forms. That's a subspace of sk of m. And we're interested in, we're here in this talk, we'll be interested in refining this set even further to pick out certain subspaces of this space of new forms. So to define the subspaces that we're interested in, let me recall that each cusp form of weight k and level m corresponds to an automorphic representation pi. So this is an irreducible representation of the group G of A, where G is PGL2. So I'm going to assume in this talk trivial central character for simplicity. And A is the Adele ring of Q. So this group has a factorization as a restricted product of local groups, PGL2R, and then the p-adic points of the group here. And correspondingly, the automorphic representation has a factorization as a restricted product of irreducible representations of these local groups here. And we know something about these local representations. They're irreducible, admissible, infinite dimensional representations. Pi infinity is the weight k discrete series. So that's how the weight of k enters in of PGL2R. At primes not dividing the level m, pi p is an unramified representation. So these are very well understood, easy to construct. They're just induced. It's induced from an unramified character of the Borel subgroup, and the parameters defining that character come from the Hecke eigenvalue of f at p. For primes dividing the level, the situation's a little bit more complicated. We have a more rich type of set of representations that pi p could belong to. So here's pi p is a ramified representation, has conductor p to the order p of m, and this could be principal series or a special representation, twist of Seinberg, or a supercuspidal representation. So the point here is that, again, a new form has attached to it a set of local representations, and the interesting ones are the ones at the primes dividing the level m. So we're going to focus on those. So what we'll do is we will fix for each prime dividing the level an isomorphism class of irreducible admissible representations. So that's on this slide. So for each p dividing m, let's let sigma p be an admissible irreducible representation of PGL2QP with the right conductor, p to the order p of m. And we will take this tuple of representations and put them into a vector, which I'll denote by sigma hat. So sigma hat is just a collection of local representations, one for each prime dividing the level. And we can ask to, we're going to look at the new forms that have exactly this prescribed behavior at the primes dividing the level m. So hk of sigma hat is going to be the set of new forms of weight k and level m, whose local representations belong to the prescribed isomorphism class that we fixed above for each prime dividing the level. And sk of sigma hat will denote the span of these new forms. So this is a subspace of the space of the new forms, and we have this direct sum decomposition as sigma hat ranges over all possible tuples in this way with the right conductors. Then we get the direct sum of these subspaces. Okay, well, we have, using the trace formula, or we have dimension formulas for various subspaces. So first there's the Eichler-Selberg trace formula, which gives us the trace, dimension, in a special case, the dimension of the full space of cusp forms of weight k and level m. Using a sieving argument, Greg Martin in 2005 wrote down an explicit formula for the dimension of the subspace of new forms. And a lofty goal, I guess, would be to refine this even further and ask for the dimension of each of these subspaces of new forms with this prescribed local behavior. And more generally, actually, we could ask for traces of Heck operators on these subspaces. These subspaces are stable under the Heck operators. So this is a difficult open problem. Via the trace formula, we can gain some traction on the problem when each of the local representations is square integrable. So that's what I'd like to talk about next. Well, actually, first, let me describe what's known with this problem. So here's some, we know asymptotics. So Jared Weinstein has proven that with finitely many exceptions, there exist Hilbert modular forms with prescribed ramification data, and he gives an asymptotic for the number of such forms. This is basically telling us that these subspaces are non-zero with finitely many exceptions. More recently, Kim, Shin, and Templier studied similar question over quite general groups, G, that have discrete series at Archimedean places. So they fixed an L packet of discrete series representations at infinity, and they fix at a finite non-Archimedean place of a number field F, a supercuspidal representation sigma. And they're looking at the count of discrete automorphic representations with this prescribed local behavior. And they show asymptotically that the number of such automorphic representations is essentially up to some constants, the product of the formal degrees of the representations, the prescribed representations that they fixed, plus an error term that grows more slowly. So that sort of tells us what to expect asymptotically. When M, the level is square free, the problem has been answered completely by Kimball Martin in 2018. So in the square free case, those we're looking for representations of conductor P. And Kimball Martin gave an explicit formula for the dimension of SK of sigma hat in that case, when each of the local representations that we fixed have conductor P. These, in this case, sigma P's are special representations or twists of Steinberg representations. And this is really specialization of Yamauchi's trace formula from the 1970s for Atkin-Lehner operators. I just want to mention an interesting application or observation that Kimball Martin made as a result of his formula. If we denote by SK plus M or SK minus M, the subspace of new forms with root number plus or minus 1, so that's the sign of the functional equation in this case when the central character is trivial, then you can add up the dimensions to compute these dimensions of these larger subspaces and look at the difference. And it's always greater than or equal to 0. In fact, it's strictly greater than 0 with finitely many exceptions. So there's the root number, which you would expect, and in fact, asymptotically is, half the cusp forms have root number plus 1, half of them have root number minus 1. Actually, there's a strict bias in favor of positive root number. And the difference between the two dimensions of the two subspaces is this constant Cm, which is just 1/2, 1, or 2, depending on M's equivalence class modulo 8, times the class number of Q adjoin the square root of minus M. But anyway, in the case where M is square free, this completely answers the question. Although I'm not sure, actually, I don't think we have traces of Hecke operators, but that's probably also doable from Yamauchi's trace formula, but I haven't thought about it. So we're now interested in the case where we're looking at local representations with higher degree ramification than the first power. So square integrable representations of conductor P to the A, where A is bigger than 1, are supercuspidal representations. So these are much more difficult to understand, but they have some very nice properties, chief among which for this project is the fact that their matrix coefficients are compactly supported. So when A is 2, we're looking at the supercuspidal representations of conductor P squared. These are the depth 0 supercuspidal representations in the sense of them having minimal conductor exponent. They're the simplest, but actually they're not the simplest to define and work with, because you have to understand the cuspidal series of GL2 FP, which is a little bit complicated. So a better first place to play around with this is actually conductor P cubed supercuspidals. These are called simple supercuspidals, and their construction is very easy. This first came to my attention from a paper of Dick Gross in 2011, which I'll mention again a little bit later. So the construction's a little bit important for what I'm going to do, and it's simple enough that I'd like to give it here. So here's how you construct simple supercuspidal representations. So these are representations, supercuspidal representations of conductor P cubed. We'll define an open compact mod center subgroup of GL2 of QP in the following way. This is going to be, this represents the matrices with p-adic integer entries that reduce modulo P to unipotent matrices. So it's the pro-unipotent radical of the maximal compact subgroup. And Z here is the center. So these are the scalar matrices of GL2QP. So this is a group, and it's going to be of index 2 in the group that we're interested in H. And the other coset representative of this subgroup is this off-diagonal element TP. So what I skipped this line actually. So in order to define a simple supercuspidal representation, you need to fix two pieces of data. The first is a non-zero element of Z mod PZ star, which we denote by T. And that's this element here. Of course, this is in QP, so you just take any lift of T to ZP star. It doesn't matter which one. And zeta is going to be the local root number of the representation. That's just going to be plus or minus 1. So from these two parameters, we're going to define the simple supercuspidal representation. So here's the subgroup H that we want to look at. We'll define a character of this group by taking a matrix that reduces mod P to a unipotent matrix. So the complex number, e to the 2 pi I times B plus T times C over P. So T here is this parameter that we fixed. It's easy to check that this is a character of this subgroup. And we'll take this other off-diagonal guy to the local root number zeta. So this guy, when you square it, you get a scalar matrix. We're assuming trivial central character, which is why zeta has to be plus or minus 1 here. Anyway, so this is a character of this open compact mod center subgroup. And if we induce that character, take the compact induction from that character of H all the way up to GL2QP, we get an irreducible supercuspidal representation, which I'll denote by sigma T zeta, with trivial central character and conductor P cubed. And conversely, all irreducible admissible representations of conductor P cubed of GL2QP with trivial central character arise in exactly this way. So we can count them. There are P minus 1 choices for the parameter T and 2 choices for the parameter zeta. And these are distinct. So there are 2 times P minus 1 such representations of conductor P cubed. All right. Now we'd like to, what we'd like to do is fix a square-free level, well, a square-free number n. Well, for simplicity, we'll assume it's bigger than 3. And we want to look at the new forms of level n cubed. So according to what we just saw in the previous slide, the new forms of level n cubed is the direct sum over all local tuples sigma hat of SK sigma hat, where each local representation sigma p is a simple supercuspidal representation as constructed on the previous slide. So from that paper of Greg Martin, the dimension of sk nu of level n cubed is k minus 1 over 12 times the product of p dividing n of p squared minus 1 times p minus 1. Now, we would like, as I said, to refine this dimension formula to get the dimension of these subspaces. Well, without any reason to think otherwise, you might think that they would all have the same dimension. I mean, we just have two parameters, zeta plus 1 or minus 1, and then these t's ranging from the finite field z mod pz. And there's no reason a priori to think that nature would favor one over the other. So maybe we think they all have the same dimension. As I mentioned, we know that there are 2 times p minus 1 such local representations. So we might expect that the dimension of each of these a given subspace would be, we would just divide each pth factor by 2 times p minus 1. And it turns out that's exactly correct, at least asymptotically. The dimension of the subspace sk of sigma hat is asymptotic to this k minus 1 over 12 times p squared minus 1 over 2, which is what you get when you take the full dimension and divide it by the number of local simple supercuspidal representations. Of course, then the next question is this asymptotic actually inequality? So this asymptotic comes from the paper of Kim, Shin, and Templier. Is this actually on equality on the nose? The fact that it isn't can be seen very easily because this actually is not always an integer. So that tells you there has to be something else going on. Back to this paper of Gross that I mentioned earlier, he looked at this, an aspect of this question. So he fixed the TPs and he varied the zeta p's. So, and he looked at the direct sum of those subspaces. So we let sigma hat fix a tuple TP, so fix the guys in the finite field and allow the local root numbers to vary. Then you would expect to just get this thing, but divided by p minus 1, which is the number of, at each prime, which is the number of possibilities for the TP that he's fixed. And he does get that on the nose as the dimension formula, the dimension for this subspace, this direct sum. A complementary thing was studied in a recent paper of P and Shi. What they did is they fixed the global root number and they varied the TP parameters. Of course, if we would expect, as in the same case that just like we did for the square free level case, we would expect half the cusp forms to have root number +1, half of them to have root number -1. So we would expect that if we look at the, say, the plus space or the minus space for corresponding to the global root number, we would expect the dimension to be the full dimension of the space of new forms divided by 2. And so that explains the main term that they get in their formula for the dimension of the spaces with constant global root number. But then they have an error term, which again involves the class number of q adjoining the square root of -n. But once again, they find in this case that there's a strict bias in favor of positive root number, which is an interesting application. Their work does not, unlike Gross and what I'm going to talk about today, where we use the trace formula, so a special case of the Arthur Selberg trace formula, they're using actually a Peterson formula for new forms which are locally simple supercuspidal using new form matrix coefficients from a paper of mine with Charles Lee from a few years ago. But their method will not give a refinement to get the dimension of these subspaces. Anyway, here's the special case of the main theorem. We'll fix n greater than 3 an odd square free number, k an even weight bigger than 2. For each prime dividing n, we'll fix a simple supercuspidal representation, sigma p. So its parameters will be Tp and zeta p of GL2QP. Then the dimension of the space of new forms with that prescribed local behavior is given in the following way. So first we have the main term, which is exactly the asymptotic given by Kim, Shin, and Templier. So there's no surprise there. And then we have an error term, which is a single off-diagonal term here. H of minus n is the class number of Q adjoint square root of minus n. Bn is again just a constant involving a power of 2, depending on the congruence class of n modulo 8. Epsilon k zeta hat is the common global root number of all of these new forms. So it's just a product of the local root numbers. And delta of t hat is it's like a Kronecker delta kind of thing. It's either 0 or 1. It's 1 if and only if for all primes dividing n, the local guy that we've taken, TP, divided by n over p, its negative is a quadratic residue modulo p. That's just a technical condition that is required for the orbital integral where this comes from to be non-zero. If this condition is not satisfied, then we get exactly the asymptotic gives us the exact dimension in that case. And in that case, of course, this turns out to be an integer. So I would like to mention that we can also treat traces of Hecke operators. I'm not doing that yet because this is still work in progress, but it's close to being finished, I hope. And we can also allow even levels and n equals 2 or 3. But in all of these cases, there are extra terms that we need to include on the geometric side. This is really the simplest case when n is odd and bigger than 3. This theorem implies all results on the previous page that was looked at by the previous authors. And the method extends in principle, at least, to other supercuspidal representations, particularly those of odd conductor exponents. So the ones, supercuspidal representations of odd conductor exponents are actually all induced from characters of certain open compact subgroups. But the jury is still out as to whether it will be feasible to carry out this program for these representations. And I'd just like to mention, I haven't done this, but certainly you could consider Moss forms as well. And in that case, you would get a Selberg trace formula with no Eisenstein term because of the simple trace formula that we use, kills off the Eisenstein continuous spectrum. Okay, and the time that's left, I would like to give an indication of the proof. I have no idea how much time is left, by the way, but yeah, you can let me know. So I use the simple trace formula. So here's a quick overview of the simple trace formula. We'll suppose f is a test function on PGL2 of the Adels. It's got to be sufficiently well behaved. It's going to be a product of local test functions, and I'm going to assume that at least 2 of those local components are discrete series matrix coefficients. Then, given, in fact, this is given any L1 function, we can define an operator on L2 of the quotient G of A mod G of Q. This is where the automorphic forms live. They're functions in this L2 space. We can define an operator on here by taking an L2 function and averaging its right translates against the value of the L1 function. So under the hypotheses on the test function here, with 2 of the constituents being discrete series matrix coefficients, this operator has purely cuspidal image, and there's no continuous term, there's no unipotent or hyperbolic term. We just get elliptic terms on the geometric side of the trace formula. So the main term is the measure of the quotient space times the value of the function at 1. And then we have this sum over all elliptic conjugacy classes in G of Q of elliptic orbital integrals, which are these integrals that I've written down here, which in theory can be computed explicitly. So it's the simple trace formula because we're missing a bunch of terms. A bunch of terms vanish that ordinarily show up in the general trace formula. So I'd like to apply this simple trace formula by choosing the test function in such a way that we project onto the space of cusp forms that we're interested in. Namely, we take at the Archimedean place a discrete series matrix coefficient of the weight k discrete series. At each prime dividing the level, we take a matrix coefficient of our fixed simple supercuspidal representation, again times its formal degree, and the formal degrees are given here. And at each prime not dividing the level, we just take the characteristic function of the maximal compact subgroup of GL2QL times the center. Then the operator that we get, R of F, is actually the projection onto this finite dimensional subspace, so its trace is the dimension. And we can tweak the test function at these other places if we want to get Heck operators. So the main term from the simple trace formula was this, you'll recall from the previous slide. The measure, the way things are normalized, is pi over 3. And we just plug 1 into the test function, and that gives us the formal degree in each case, which is this product, and that gives us the main term. So the dimension of the subspace we're looking at is this main term plus elliptic terms. And of course, the difficulty in this project is to evaluate the elliptic terms. So the elliptic terms, if gamma is elliptic matrix just means that its characteristic polynomial is irreducible over Q. It factorizes as a measure of G gamma of A. G sub gamma is the centralizer of our element gamma, mod G gamma of Q, times a product of local orbital integrals, which are defined in this way. And then with a little work, we can do some global considerations to figure out which gammas we need to look at. In fact, there's only finitely many gammas for which the orbital integral is non-zero. In the case that of the theorem, special case of the theorem I mentioned earlier, there's only one. And so that's why we only have one off diagonal term, is this matrix 1 minus n, whose characteristic polynomial is x squared plus n. And for other cases of levels, we have these other guys that we need to consider, but let's just focus on this one. And this is my last slide. I don't know how much, I guess I'm probably out of time. Anyway, so here's the dimension formula. This is the orbital integral. And there's some nice classical calculations that come from computing the orbital integral. The measure term here comes actually right out of Tate's thesis. It reduces basically to computing the volume of norm 1 EDEL class group. So that's where the class number comes from. And the local orbital integrals are, well, we get -1 to the k over 2 at the Archimedean one. And here's what it turns out to be for the other various primes. But by far, the biggest technical input into this paper is computing these local orbital integrals at the primes dividing the level. In the case where the level is even, in one case, it's about 10 typewritten LaTeX pages, the calculation of the local orbital integral, even though the result is simple. Okay, I think I'll stop here. Thank you.
Thank you very much for your nice talk.